The first of the two talks is called Nash Mean Field Games, and that's the overall title of what is a relatively new subject in the area of systems and control theory, and of course cognition and control, which I understand this series in which this series is placed. So we're seeing how the technology works here. We've just been given a I think I may have to. Yep. Okay, it's working. There's just a time delay here, so there's a time delay test in this. So I think, because that's causing enough confusion, we will put the higher technology on one side and gracefully degrade to the next picture, which is to my co-authors, Minyi Huang and Roland Mallarmé, who've been my co-authors on almost all of this work, and in particular on the pioneering papers. Now, these are the collaborators and students. Armand Kitskale, who is a co-author on work which will appear at the end of this lecture and in the second talk, and Mojtaba as well. Zhongjing Ma and Arthur Lazate are key players. In particular, Mojtaba's work will be described in the second talk. Now, the overall objective is to develop a theory of decentralized decision-making in stochastic dynamical systems with many competing or cooperating agents. Previously, cooperating was an exaggeration because it was a competitive theory or a theory of competition, but now we can seriously, honestly say that we cover cooperation in our theoretical framework. So the outline here will be that I give a motivating control problem from CDMA uplink power control and some motivational notions from statistical mechanics, which I hope you'll find interesting and entertaining and even motivational. Then we'll present the basic mean field theory for linear quadratic control and explain the game theoretic aspects of this and the principal theorems. Then I think we'll go on to describe an adaptive version of this theory and possibly, time permitting, go to the leader-follower theory, which is one of the branches that have developed in this framework. So this picture, which is a bit faint in this projection, is supposed to indicate a group of CDMA cell phone users and a base station on a tower, which is definitely almost invisible here. Now, the problem is that the agents have got a noisy channel connecting them to the base station, and the quality of the channel is measured by this stochastic differential equation. Now, I know that not all of you have studied stochastic differential equations, but a two-line introduction to this theory, which is all that we'll need today, well, to begin with, is that if you take out the noise increment here, this is a classic ordinary differential equation. Now, here we have an increment of Brownian motion, and the reason that the equation must be written in this form is because it is the differential version of the corresponding integral equation, and the steps here of dw, the increments in the Brownian motion, are of order root dt. And this is why the Ito stochastic differential equations are in fact a genuine, dramatic extension of the Leibniz-Newton calculus. So this introduces a random term whose order is of the square root of dt. Now, the transmitted power across the channel is the product of the channel attenuation, which is the exponential of the state variable xi here. This is on the ith user's channel, multiplied by the power, where pi is regarded as a control variable. Now, so this model is fairly well established in the communications field, and this here being described in a paper by Bambos Charalambos and Nicky Menendez. So now a standard measure of the quality of the transmission is the signal to interference ratio, and this is for the ith agents. Now, this is where the competitive feature of the whole business comes in. So at the base station, the SIR is given by the ratio of the transmitted power for the ith player, this is all for the ith player, divided by the average of the transmitted powers of the other agents plus a thermal noise term. Now, you can see that when n is large, we get pretty much the same thing if we include the ith player in this average. And why do we get an average? Well, this is the nature of the CDMA encoding protocol. Now, the question is, how do you optimize this quantity for everyone? You see, if simply the ith player decides to gun his or her power in order to get the best SIR at the base station, then everybody else can decide to do the same thing. And so what will happen here is that the ratio will remain roughly constant. So it'd be as though we're all here trying to communicate, and we shout louder, but in fact we cancel each other out and we're just working harder. And this actually has got a name in social psychology, which is called the, well, the problem is the cocktail party problem, and the sort of solution to it was called the cocktail party effect, which was studied back in the early 60s because of problems in air traffic control towers, and there was a question of this hubbub of the various air traffic controllers speaking to different pilots. However, it was noticed that they could lock on quite effectively and, in fact, eliminate to a significant degree the interference from other air traffic controllers in the same room. And the reason was that they could actually tune their hearing to the frequency of the pilot that they were wanting to speak to, or in the cocktail party, to the frequency of your friend's voice. And after that, you sort by subject. I thought it was semantic, but in fact, it's actually done by frequency by humans. Now, the question is, how can we actually maximize the sum of these SIRs, which would be called the social welfare function, in an economic context? So since centralized control is not feasible for this problem, because you have to have everybody communicate with everyone, negotiate and all the rest of it, with hundreds or thousands of users, this is not feasible in real time. Is it possible that these systems, these sorts of competitive large population systems, can be optimized using decentralized control? And so that's what this theory does. We use large population properties of systems together with the basic notions of game theory to come up with a theory for what is at first completely decentralized control. And in fact, it'll have a rather counterintuitive feature that, we're trained as systems and control theorists and engineers to always look for feedback with to get the most information that one can about the environment with which one's interacting, and then to exercise feedback with respect to all of that information. But you see, this isn't feasible here, and what we want to do is the best possible by, with the smallest, with very restricted information. So that'll lead to some counterintuitive features to the solution. Now, the fact that there are large population properties which are simpler than those of the individual agents is familiar to people who've looked at, who've know anything about statistical mechanics, which, quite frankly, we didn't to begin with. And so we're trying to find, we would have made honest efforts to learn something about the background of the subject we're trying to use, or be motivated by. So there's going to be a brief segue here through statistical mechanics, which is supposed to motivate everybody in terms of looking for bulk properties of large numbers of interacting agents. Except here, these are not yet agents, because there's no self-interest of any sort for particles in gas molecules in a jar. Okay? So I remind you that the foundation of thermodynamics was provided by statistical mechanics, by Boltzmann, Maxwell, and Gibbs in the 19th century. And the basic ideal gas model describes the interaction of huge numbers of essentially identical particles. So what you'll see here is that if we take, and this is a two-dimensional model of interacting of particles which are bouncing off each other. This is a billiard ball model. And what we've plotted here, they start off with equally distributed energies at the beginning. So you'll see that there's an effect here. And so here we go. Oh, the music's working. Okay, there's appropriate background music for this to give you the mood. Okay, so and you see these particles are bouncing off each other, and you'll see the energies come to distribute themselves in a very specific way. So so here we start from the equations of perfectly elastic hard sphere mechanical collisions of particles. And there's a transition from, and this is Boltzmann's original calculation from Paul's notes and all the rest of it, that you have velocities before a collision, then there's a satisfaction, you must satisfy each, in each collision, there's a preservation of momentum and conservation of energy, but there's also another ingredient to this, which is actually the angle at which the particles bounce off each other. In fact, they have to put in more assumptions. And subject to assumption that there's chaos before any collision, then as the particles come out of a collision, one can calculate the change of the probability of the velocity, the positions and velocity probability distribution over the whole mass of particles. And this is the celebrated Boltzmann equation. And here is the term which describes the interaction of the terms of the particles. Now here there's an integration over the variables that you can see here, over the volume, so integrating over the angles of interaction and so on. This is Boltzmann's term, and this on the left-hand side is essentially a part of the Kolmogorov equation for the evolution of the probability distribution at the instant t of the velocities and the positions of the particles. Okay, so what comes out of this is the celebrated, there's a lot of celebration here. What comes out of this is that taking the formula for entropy as given here, then one can show that from the evolution equations that entropy increases for the whole bulk of particles over time. And so this was, in fact, this led to a stupendous debate in the late 19th century between physicists, mathematicians, over to how on earth was it possible that with a system which was microcosmically reversible, one got globally irreversible behavior. So this was and in fact, when you first come across it, it still is a great conceptual challenge. So Boltzmann's equations actually revealed a mass behavior which was of immense significance, namely the increase of entropy through the evolution of the dynamical interaction of the particles, when microcosmically one had reversibility. So what this is supposed to, and let's just now have a look so the moral is extremely complex large population particle systems can have simple continuum limits with distinctive bulk properties. And so that's the first step of the talk. And we can see this slide again with, again, an energy-related background music. And so if you watch these particles, they're rather faint here, and you'll see them bouncing off each other. So it's a billiard ball model. You have a uniform distribution of the energies to begin with. And you'll notice that as time progresses, then the profile here becomes Gaussian, which is called the Maxwellian distribution, which is the steady state maximal distribution which will maximize the entropy. Okay, so so the distribution we get to will be Gaussian, and that in fact is illustrating the steady state maximization of entropy for the system. Okay, and there's, as I say, energy related theme song here. So here we are. See. So here we are converging. See, and this is now got onto into a discrete semblance. Okay, that's the energy part. so what we're going to do, the key intuition here, as I've said, is that large mass of individuals may be treated as a continuum, and that the local, well, there's a further illustration actually for this part, which I'm not going to spend time on, but that local control can then result in the shaping of the global behavior. But there's one crucial difference between molecules that are interacting and agents in the complex systems which we want to analyze in large cybernetic systems. A word which we all agree should be reintroduced into our subject. So, of course, the point is that in systems and controls theory and systems which one's engineering, there is a cost function. There would be a performance function. Now, we're used to optimizing trajectories of space vehicles, aircraft, production plants, vehicles, terrestrial vehicles, economic models, valid or not valid. And so the optimization of systems when there's a single performance criterion is a very familiar subject. It has been the topic of optimal control since the 40s and the 50s. Now, what happens here, though, is that we're going to have large ensembles of agents, each of which has its own performance function, so which will reflect self-interest before we get to the fancier questions of cooperation. So these will reflect individual interest, which gives the whole analysis a special flavor, a more general flavor than standard control theory. And in fact, leads us to use ideas from game theory. So let's go to the basic model that we're going to use. It's an extremely simple model, but it will carry the key ideas for the development for most of the rest of this talk. So now, instead of having the dynamics of bouncing molecules or interacting billiard balls, we're now going to go over to a elastic system of the sort that you saw in the CDMA motivating example. And here we've got the explicit control coming in linearly. There's no exponentiation because that was a specific part of the gain model for transmission links. So this is simply linear quadratic Gaussian theory. And we're only using the scalar case here for the simplicity of notation. And so there's buckets of notation to come. So and certainly in the second talk. So it's a sort of light relief here to be able to treat the scalar case. So here's the individual's dynamics. And as usual, xi will be the ith agent's state, the control, its disturbance, where all the disturbances at this stage are independent, and n is the population size. So now you notice that at this stage, there's no interaction between the agents, except for that which might be introduced through the control. So I mean, there are many meaningful large-scale system problems where the issue is how other agents' dynamics, states, will impinge upon my dynamics. And we'll see that later. But right now, please note that the equations, if I make ui deterministic or purely a function of xi, then the agents are statistically independent. And in fact, after we finish, they will in fact end up in that state again. Now, here is the problem that we're going to solve. Here's the individual's cost function. So as I said, the demarcating feature here, the characteristic property of the problems we're looking at is that each individual has its own, each agent has its own cost function. And this will look cooperative, but in fact, it's formulated as a competitive problem. And so the problem here is that that the ith agent wants to approximate the mean of the other agents plus an offset. However, it will not be allowed to see what the other agents are doing. So that's the catch. Because if you guess that everybody here is going to take a low trajectory, and so you go for a low trajectory, But if the others had all colluded or by accident decided to take a high trajectory, then you're going to end up scoring a high cost for that difference. So it's non-obvious what's going to happen. Now, you square that error, your control effort squared, so you've got here a measure of your power. This is run over a long period. This is discounted, so you get a finite number. So again, something familiar, for instance, from economics. And we take the average of this because the trajectories are random. So the agents in this problem are only coupled through their costs at this stage, not through anything else. So it's only through the costs. As I say, all of this gets massively more complicated later, but we get the key ideas at this stage. Now, this may look as though it's a rather simple and perhaps undermotivated problem. However, versions of this problem appear in economic models, advertising competition models, wireless networks, admission control and communication networks, public health, biology, sociology, and renewable energy. These are the list of authors. Because of limitations of time, I can't even go down into the particular issues such as swarming or vaccination games in any detail except to point to them, and the attributions are here. So, I hope that this will give you an impression that this sort of problem formulation is of wide applicability, and that I think accounts for the fact that it's becoming an extremely popular area of research. Now, it's important to note that over the last 40 years of work, there has been a great deal of work on stochastic dynamic games and team problems. And so, again, there's no way that I can cite all of the authors concerned, but going back to the Witzenhausen's celebrated counterexample, more celebration, celebrated counterexample in the 60s, and then work by Varaya, Larry Ho, Tamer Bassar, and many others, that the problems of information and control, often in a game theoretic framework, have been studied in depth. However, none of those works, it's fair to say, are actually considered large population problems. And the finite population problems that occur here are extremely complex. In fact, that's why it's called the Witzenhausen counterexample, which is actually a team problem, has fueled research for the last 40 years. It's a source problem. Now, what happens, because of the sort of bulk effects that you've seen, because of the smoothing effects, that we can do an end run around the great complexity of finite cardinality stochastic dynamic games by going to large population games. And it's that gives us our leverage to solve these problems. Now, because I've indicated that this work is becoming very popular now, and so I'll just mention briefly that others who saw in the early 2000s that one could use large population analyses were the Markov models with oblivious equilibrium group, and that's and again Weintraub, Benkard, Roy, and their associates. This was in the business school community, using Markovian models rather than diffusion models. And that gives rise to a different mathematical style of analysis. Then there's the Parisian school of Lazary and Lyon, who in the middle 2000s discovered that what is called mean field game equations. This was in the nonlinear setting contemporaneous with us, but years after our initial work on the complete LQG theory. There's the mean field control of oscillators by what we previously called the Illinois 4 or the Illinois 5, or the Gang of Four. Those included Professor Mine, who is now here. So since your Mine is here, this has to be called the Illinois 3 or the Illinois 4, as they've lost one person. And then there's the application of mean field Markov decision processes to games on networks. And then this is again by Hamidou Tembine and his associates. So I hope this gives you an indication of the ramifications of the large population approach to complex control problems within this framework, within what is called now the mean field games framework. So let's go back to providing a solution to the problem that we posed earlier. So now, the way it's done is as follows. That forget the game theoretic aspect for a moment and just think of one player, classical linear quadratic Gaussian problem, of one player that is trying to track a deterministically given signal x star. Okay, so this is given to you. It's a sinusoid or whatever. Then, what is the control action that minimizes this loss function? The answer is, which has been a solution to the tracking problem, and it's in textbooks, you can, it's been known for decades, then you solve the Riccati equation, which is a steady state Riccati equation of linear quadratic control, where the discount factor appears on the left-hand side here. Then, now these are the key modes of the resulting system, and for all small enough rho, it will be the case that this mode here will be stable, which corresponds to beta 1 being positive. Now, the control action is the following, and it's quite easy to understand, that if you were not tracking a signal x star, but just carrying out standard LQG control, where you want the state xi to come in as close as it can to the origin and to remain there, okay, well, of course, it can't remain there because of the disturbing noise, but that you want to carry out optimal feedback control with respect to this loss function, so that is to say you minimize it, then as most of you probably know, that you apply state feedback of this, so to speak, negative state feedback proportional to the state, where the gain has the key term in it, pi I, which is a steady state solution to the Riccati equation. So it'll be negative feedback of the state. Now, if there's an offset x star, then there's namely you're tracking x star, there'll be an offset to the LQG control. And that'll be given by this signal SI, and it's I here for the ith agent, even though we're isolated. And SI is obtained by the solution to this equation, which is driven by the signal that you're trying to track. So what you do is you set up the problem, then you solve this equation over the current time to plus infinity. Actually, you have to integrate this backwards because it's unstable in forwards time. You get your ST offset signal for the agent I, and then you put this into the linear quadratic feedback control in the following way. And that gives you the optimal, your optimal control for the tracking problem, discounted tracking problem. Now, here's the idea. The idea is that in the previous problem that we were looking at, that the mass x star that you were trying to track, which were the other players, is now substituted by what the other mass of players would look like if they had all chosen a particular control law, which is optimal for them individually, and then they would look like a massive deterministic body, a wave moving, whereas locally you look like a stochastic system bouncing around because of the intensity of your own noise. You see, in the problem when we formulated it, there was an average here. We had 1 over n, the sum of the other states. So that would look like, or could, if they adopted predictable control laws, a wave motion, something deterministic, that then you could react to with this control law. Then you get into the interesting loop, the magic circle, if you wish, of game theory, which is if you're all doing that, then, and if you believe all the others are doing it, rather, then it's best for you to continue doing it, so that this is a reproducing stable situation, which is optimal for yourself. Now, I'm going to make this precise, but that's the idea. Okay? So we've got the control for deterministic x star. So now, and the nature of the control is that you're playing against the mass. All of the agents here are playing against themselves, and then hence have an influence on you. but this group will look like, like a predictable environment if they're all following a specified control law. So this is now the resulting, the local state feedback will be the negative feedback to your local state, okay? So this is the minus control gain times xi, which will be stochastic, because locally your environment is stochastic, but the feedback of the deterministic mass will be that offset Si, which will be just that, deterministic. Okay. So notice that in contrast to other large-scale systems analyses, or before this theory, where you lost all individuality of the individual agent, for instance, as in the gas dynamics, that the individuals vanished, here we retain the individuality of each agent with respect to the continuum of other agents in the infinite population limit. Now, now what we do is we now give a prescription for a way that each agent would calculate the optimal tracking control if it were the case that the other agents were all doing the same thing. So so here we go, that we've got a continuum of systems. We assume that all the other agents will be applying tracking control with respect to the x star, which they can compute, which will be the mean behavior of the mass. So everybody, including yourself, solves this array of equations. Here's the S equation that you saw before for the 8th agent. Now here's x star. Before it was a deterministic signal, and it goes in here as a variable. Now here's the stochastic averaged behavior of the 8th agent. Here there is a point which is in some sense technical here, because the different agents can have different dynamics, different parameters. So we average over that. If they've all got the same parameter, you won't have to do that. Then we concoct x star now. All these equations are deterministic, nothing stochastic. Then we write x star as gamma times, which is what appears in the loss function, x bar t plus eta. So this is the x star that appears in the loss function. So you see, and then this is the Riccati equation for each agent. Then now, if everybody was solving this set of equations, then your control action would be just as I described before in the tracking problem, but here the SA would be produced by this equation for you, driven by the x star for the mass. So now there are questions which come up, which is, firstly, does this set of equations have a fixed, does there exist a solution for everybody for this set of equations? And the answer is yes, under reasonable conditions. So everybody says, oh, the conditions for my theory are reasonable, and the hypotheses are not too demanding, and sometimes there's skepticism is merited there. But in this case, it's true. The hypotheses are reasonable. So now, okay, now, so we go back to the problem we were trying to solve, or that we are solving, which is that we have the individual stochastic agents, then in game theory notation, then the actions of all the other agents will be u minus I when viewed by the ith guy. So the ith agent's loss will be a function of its control ui and all of the other agents' controls. Now these are control laws, notice, okay? And here we have the fully displayed loss function that each individual agent is trying to minimize. Now, the algorithm, the control algorithm, as I've said, is the ith agent will compute its control using the x star from what we call the NCE, Nash Certainty Equivalence Equation System array that we saw before, and then it will solve for its own control. Okay? Now, so far, we've got a problem. We have a proposed set of controls, and now the question is, what is its properties? Now, that we need to do like a three-sentence introduction to game theory here, which is the notion of a saddle point Nash equilibrium. So this is super faint, but the idea here is that for players, first player has got to control x, second player y, and we've got here a zero-sum game. Now the agent y is a maximizer, so that it wants to move as high as it can, and the agent x is a minimizer. Okay? So if we consider the control actions 0, 0, okay, then X has played 0, so it's forcing Y to move over this hump in the saddle. Now, Y is a maximizer, so therefore Y will play 0 in order to get to the seat in the saddle. Similarly, if Y is playing 0, then X is a minimizer, so Y is forcing X to get a loss that looks like this, so it will play 0. So we have, therefore, what's called a Nash equilibrium, where if the other agent plays the prescribed control, then it's to your disadvantage to play anything other than the prescribed control. So now we're dealing with this. That was the most simple illustration that one can possibly have of the notion of a Nash equilibrium. We're dealing with a much more elaborate situation here. We've got stochastic dynamic gains. So we have to have the information patterns, and using the jargon of control theory, where we say the sigma field generated by, this just means the information carried in, the trajectory of the ith agent. So this is written Fi, so that's the ith agent's information up to t. And then this is all of the agent's information up until t, taken together. And the controls, and this is the information and control aspect, the ith agent's control is going to be only a function of Fi, and F in there is the overarching set of control information. So the equilibrium that we're going to be looking for is that to take the set of controls which are going to be this is a definition that we have a Nash equilibrium with respect to these costs for this set of controls if, when all the other agents play their control actions from this set of controls, then your action in this set gives you the infimization with respect to your free control. So it would be damaging to you to do anything else than to play U0I in the specified set. Now, there's an extra feature to this, which is that we've stated that these controls are local. This is the distributed control aspect, are local in the sense that the ith agent's control depends upon Fi. But what we're going to be looking for is a strong property that you are allowed to deviate by using controls which depend on all of the information you could possibly get your hands on up until t. Okay? So your Nash move gives you a much more scope than, in fact, that you were given when the UIs were calculated. And we're going to see that we have this strong form of Nash property. Right, now we now have enough. And the epsilon Nash equilibrium is just what I've said. Oh, epsilon Nash equilibrium means that what I've just said before is true up to epsilon. Okay, we'll see the role of that in a minute. Right, now here's the basic result, and all of the results to come have got this nature. So this theorem, if you wish, is the robust theorem for the theory. This is the kind of result that we get in more and more elaborate situations. So, subject to what I've said, are reasonable technical conditions, the NCE equations have a unique solution for which the NCE control algorithm, that was the specification of the control, generates this set of controls which form a epsilon Nash equilibrium for the whole system. This is in the sense, well, firstly, there's a stability for each agent in a specified technical sense. And we have an epsilon Nash equilibrium in the following sense, that the relationship here holds up to epsilon, where epsilon goes to 0 as the population goes to infinity. So here's the key thing, that even if you're playing with 100 players or 1,000 players, 10,000 players, you calculate your feedback control using the NCE scheme, which was formulated for an infinite number of players. This is a key notion, that you don't try and solve the problem for a large number of players. We know that's intractable for like 7 players, let alone 700 or 70,000. What you do is you go to this smooth set of equations for the infinite population. That's tractable. You saw the equations. We can solve them. You'll see that in a minute. And then each agent will use its own pre-computed controls from that set in the large, finite player situation. Now, obviously, that isn't going to be exactly an exact Nash equilibrium. That's right. it'll be epsilon off that, epsilon away from that. But that epsilon will go to 0 as the population goes to infinity. A question?
Two quick questions.
Right.
Is
Yes. This is all the tracking problem still. Yes.
in your definition of the Nash equilibrium, where does X star come in? I didn't see any role for X star. It was only locally adapted. So where do you use X star in the definition?
Oh, so let's go back there. So so what we've got is the J's here, the J's, right? So the J's are computed with total expectations, no total expectations. So you see, when I specify the J, let's retrieve that, your control has that information restriction, but your loss has a total expectation here, you see. So these guys have all, these states, in fact, that they are going to end up with, their controls are going to be depending actually on their own observations of themselves.
I think that's in the solution, but not in the description of the problem. So when you say that, go to the next one.
Yeah, sure.
Describe the optics. Yeah, so in this definition,
Yes.
your U0 does not have any X star in it. And the set of controls adapt cap U0.
So, well, X star has, the X star that you saw just now was the X star, it was the X star from the SCE equations. And that is a deterministic quantity. So it doesn't have to be measurable with respect to anything. So you see that in fact, the UIs are indeed, you see the UIs you get, so let's go back on that. So the control that you actually get, so this is the LQG tracking. Let's get to the actual stochastics. You see, here's the stochastic control that you will be applying. You see, you've all solved this deterministic set of equations, and your control here will depend on your own state, which is in this case, FA measurable, okay? And these quantities here everything else is deterministic. So there's no measurability question there. And the actual loss function, which the loss function, just to repeat, is computed with a total expectation over everything. Okay, so it's completely consistent.
I hate to slow you down, but in practice, if you've had that global average, you might do that for finite.
Oh, notice we do not claim, you see, for finite n, that this is the claim. The claim's the claim. So I'm not going to supply more than the claim, you see. And so this is going to be exactly Nash only at infinity. Okay. So now, this is this is a robust theorem because you're going to see that holds in many situations. Now, I'm going to have to do a time check with Sean as the MC. Well, I'm certainly not going to push the poor audience that far. Go on, keep going until we're thrown out. I think if we just keep going, I think the audience may throw me out. Okay. And the next talk is at what time? 1:30. Oh, the next talk's at 1:30. Okay. Well, so we get a continuum. Okay. So, but we'll try and wind up in not more than 15 minutes. Okay. So if anybody wants to run screaming from the room at 1 o'clock, then that's okay. That's allowed in the etiquette, seminar etiquette. So, so now I've just actually all of these points have been mentioned. That the information set is minimal, and so do notice that this is the counterintuitive feature. So it's worth spending repeating this. Is that this Nash equilibrium is achieved in a completely decentralized way. Although you're going to be dealing with 350 other agents, up to epsilon, using this control law, you get the best, epsilon best that you can by solving that deterministic set of equations, the deterministic solution, at the beginning before you start, and then just looking at your own state. Now, this is not completely unusual in control. Suppose you are in your space shuttle, then you do compute a deterministic path, and then given that this is your optimal deterministic path, you do stochastically servo around that as you go through the atmosphere. So having a global criterion or a pre-computed criterion which is deterministic, and then a stochastic behavior, which is in some sense optimal around it, has been a foundation for the formulation of systems of control engineering solutions forever. Okay, so it's forever meaning dating from 1945.
Before you move forward, of course, this is the resulting proof, right?
Yes, this is a theorem.
Yeah.
That's a theorem.
It's not possible these solutions, in fact, converge to the actual Nash equilibrium.
But only in the...
Without an epsilon.
I think that would, in general, no. No, in general, no. No, so it's unfortunately the answer. It would be interesting if we had counter-example, such special cases, but no. So now all of these points have been emphasized, and now we get a very that there are many extensions of this, but one is where we introduce, in some sense, distance between the agents, because up until now there's been no geometry. Now you can actually introduce that a decay effect in the cost function for each agent, so that agents that are in some sense far away influence your cost function with respect to them less than those that are close up. It's a natural thing. And then the theory goes through again. I'll just say once that all of the work I'm describing here is published in referee journals and so on. So it's the stuff in the second talk, which is only in conference form. So here we have a decaying cost function, a decaying weighting. I won't go into technicalities of it, but it does have a rather beautiful illustration, which you can call the Berlin Wall or the Great Wall of China model. Actually, this reminded me really more from the flea markets of Berlin than the Berlin Wall, in the following sense, that what we're going to have here is two collections of dynamical systems of the sort that you've seen. They're on this two-dimensional array, and they're going to first solve with respect to each other with these decaying influence functions. They're going to solve the NCE equations, and then they're going to be in a mean field game equilibrium. The key feature about that is you'll see indeed that the agents are still stochastic. They've come into an equilibrium with each other with respect to the loss functions, but they're still bouncing around because there's still local noise. And that'll happen with the two systems here, which have got slightly different parameters. So so you'll have one mean field equilibrium here, one mean field game equilibrium here in disconnected worlds. Then at the 20th second, the glass wall is taken out, or the markets are joined up. They'll recompute their solutions, and then you'll see that the guys here have to take account of their neighbors, and so they'll sort of come in towards each other because it's a distance that you want to approximate the states of your neighbors. There's also going to be a curling effect here, but that's an artifact of the computing. It was done on a torus, but for reasons we're going to. So what you've got to do is to see how quickly the system comes into its NCE, or mean field game equilibrium, and then wait a bit, and then you'll see that there'll be a response to this community realizing this community exists and recomputing its solution, and vice versa. There's a musical accompaniment. So here we go. So here we are, sliding into. So you said come into their MFG equilibrium, and notice they're still bouncing around, right? There's still local noise, you see? And so this is what an MFG equilibrium looks like. You see that they've got local noise, and then if you look up here, 20th second right. So now they've recomputed, and these guys are aware of these guys and vice versa. And so they're coming in and responding to each other, and now they're in a new equilibrium. Okay? So these marvelous simulations are due to Armand Kitsakale and Arthur Luzzati, okay, who you saw earlier. Okay. Isn't that cool? It's just remarkable, eh? So then we'll get to the 20 seconds, then we'll move on in the theory. Okay. So here it is. So as we get to the 20th second, you'll see, bang, they recompute, and then they adjust to each other. Okay. Right. So.
What did you do when it hit 20 seconds?
what happened was that the cost functions of all of the agents were changed, taking account of the existence of the other community. But since the cost functions dropped off, those who are away from the edge, it didn't affect them. But those who are near the edge, where there's a contiguous contact between the two communities, they had to adjust to each other. And that's why they came in. Right, so now, that's right, there's an indexing. That's right, we have to introduce an indexing, and the indexing goes into the cost function, and that corresponds to adjacency. So I didn't take you through that because it's purely appears as notation. That's right. So we have to give the agents then get an individuality, which is not only you're the 20th agent, but also you're in the 3,460th position. And then that gives a sort of a form of metric. Now, the
X star becomes spatially distributed, right?
yes, I mean if you compute the mean field, which is what that is here, then indeed it'll be distributed, but it'll be in each community. Before you do that, it'll be even in each community. Then it gets distorted by the fact that the other community will have different parameters and it has to adjust across. So there you actually do see, if you wish, a visualization of a mean field, indeed, which will be the average state locally. So, which would be shift invariant and hence global before you join the communities. Now, the next part of the talk, which we'll try to present efficiently, is the question of adaptive control. So the information, just to repeat, is that the information which is coming out, the information which is required to solve your, these problems is your own parameters, your own cost function, and you'd need to know the cost function of the other agents and the parameter distribution of the other agents, not their states. You're not allowed in this formulation to observe the states of the other guys. There's just too many of them, and it's inherently impossible in many of the problems we're thinking of. But you do have to know a profile of the distribution of the states, the distribution of the dynamical parameters of the other agents. Now, what happens if you don't know that? Well, then by observing a fraction of the other agents and looking at a random selection of the other agents, it is then possible to estimate the dynamical parameters of a group, of a representative sample of the other agents. From that, you can then make an estimate of the distribution of the parameters of all the agents, and then you can use that in the SE equations, and then you have an approximation to your NCE control. So this gets a bit elaborate, but if you we'll just go through this here, that you observe the ith agent will observe its own state, its own control, and a random sample of the other states. And this is going to be asymptotically vanishing in the sense that the cardinality of the observed set over n goes to 0 as n goes to infinity. Okay? And so you're going to estimate your own parameters, and then you're going to form an estimate of the distribution of the other agent's parameters. And that in itself will be a parameterized distribution, so it's really effectively this parameter which you're estimating. Now this requires a concatenation of adaptive methods, and since we're doing adaptive control, then we're not going to use the discounted function that you saw before, but we're going to say what's called a ergodic, although that's not strictly accurate, but a long-range average loss function of this form. And before I omit to mention it, the generalization or the version of the theory which I've just described to you to this case with long-run averages is due to Lian Zhang of Academia Sinica Beijing. And that appeared also 3 years ago in Automatic Control, IEEE transactions. So now, here is the prescription. It looks complicated, but what it actually says is precisely what I've just said, that each agent estimates its what we call self-parameter, and then by using a maximum likelihood method, it estimates the parameters of a sample. That's the actual the A's and the B's, and from that it estimates the population distribution of parameters. And then, and this is all supposed to be in real time or at sample time, then it will solve the NCE equations and produce its own control law. And everybody is doing this. Everybody is doing this, okay? So that the ith agent will solve its own, even its estimated Riccati equation, because the Riccati equation depends on its own parameters, and it even has to estimate those. It has to solve the mass offset control, the NCE equations, with estimates of its own parameters and the mass parameter distribution. Okay, and then this is the control law which is then used, and there's some technicalities here which I won't take you into to ensure that you get asymptotic convergence of the parameters. So the parameter estimates. So those subject to the hypotheses I've described, okay, this is the procedure which I've just articulated. Estimates, compute the control law, and the result is indeed that each agent asymptotically will in fact produce the Nash epsilon control. So here we have the implications as t goes to infinity, each agent will estimate its own parameter consistently, that is, it will be exact in the infinite limit as time goes to infinity, that the population parameter distributions will be estimated almost surely as the population and time goes to infinity. Okay? So as the population must become large for that to work, as well as time to go to infinity. And we produce a set of controls which will have the epsilon Nash equilibrium property. That is to say, you see, this is the solution that we had just now when you knew the parameters. This is the loss that will be incurred at infinity for that. This is at infinity time for the agents as n goes to infinity. Actually, as n goes to infinity, and these are the this is the adaptive controls. So these controls here are the result of the estimation and feedback law, which I've just described to you. Okay? So over here, all the parameters were known, but not the other agent states. And over here, nobody knows any parameters to begin with, not only their own. But asymptotically, as time goes to infinity and the population gets very large, then within epsilon, we've got an epsilon Nash equilibrium. This is a statement for infinite population, despite that n there. But the theorem is that we have the epsilon Nash equilibrium. Now, I'm going to show you a simulation of that. So in this simulation, you've got 400 agents. Then here we've got the system matrices. So the system matrices will be these constants plus these independent Gaussian distributed random variables. So that this generates the population of A's, which have to be learnt. Okay. So this gives you the population dynamical parameter distribution. Okay. So this is what has to be learnt by the various agents about the population, and here are the population distribution parameters. So these are the quantities these are the statistics which have to be learnt. So all the agents will be performing individual parameter and population distribution parameter estimation by the procedure I've described. And now that I've said that the number of randomly observed agents will be a decreasing fraction. Here we take square root. So for 400 agents, you only get to observe 20 other agents. So here we have got to see 400 agents taking 20 other guys at random, estimating their parameters, a small fraction of the parameters as they see the trajectories of the other agents, performing this calculation, solving the SE equations, and feeding back the whole lot. And then what we're going to see, so these are various sort of statistical data showing that it works, but more dramatic with musical accompaniment is the set of trajectories that you're going to see here. So this is the final state. What you're going to see is 400 agents trajectories bloom out. The learning period is over here. We were discussing yesterday the dual control, the learning period, and then the control period. Okay, so there'd be this lock-on, but there's no analysis of dual control in the old sense. But you can see the phenomenon that the learning will take place here, and then the whole mass of agents will then be in their equilibrium trajectories, and there's a musical accompaniment. So this is the learning phase. You see? So this is the adaptation. There are like outliers crashing around. It's random, right? Okay. And so then now the population is stabilized. And so now you see what for them is their mean field gain behavior. So now and here we have a repeat. Okay, so you notice that the stochastic behavior of the population trajectories, some guys are right in on the equilibrium behavior, others it takes longer for them to converge to the mass, and then this is the NCE mean field gain trajectory. Okay, so now I'm not going to go through leader follower as promised. We'll now there are various other adaptive versions of this. This is where one's estimating between discrete parameters of the of subsets of the population, a leader-follower situation. You lock on to the correct parameter. This is another talk, and so I'll quickly summarize here that so the NCE theory solves a class of decentralized decision-making problems with many competing agents. Cooperation will be in the second talk. The asymptotic Nash equilibria are generated by the NCE equations. The key intuition is that you have stochastic local control plus feedback of a deterministic global quantity. The theory is, I'm stating, we saw the localized problems with the Chinese wall, the Berlin Wall illustration. That there's the stochastic adaptive versions, which we've been through. And then the theory also extends to what I'll do in 15 minutes' time. The egoist-altruist theory, major agent, minor agent theory, flocking, and point processes in networks. So the second concluding slide is that Minyi Huang, who is the first author, whose picture you saw right at the beginning, has made a really remarkable breakthrough in that he's been able to add major agents to this theory. Here the whole context was that of having a continuum of agents and then extracting possible predictable behavior of the mass subject to their Nash controls, subject to their NCE controls. And then Minyi has been able to make, as I say, a brilliant contribution of analyzing a situation where there's a major player. So this, the economic analogies or interpretations of this are obvious. So you have a continuum of small players and major players who are competing or even cooperating with the massive players. And this results in a remarkable extension of the whole theory, because everything that I've been saying that is predictable and deterministic about the mass behavior up until now becomes stochastic because it gets pulled around by the behavior of the major player. So it's a very significant generalization with many ramifications, some of which of our explorations in that I'll describe in the second talk. So now, what I see is that what I haven't shown here is the nonlinear equations. And so the version of the slides with the nonlinear equations, I can show those. It requires some description, so given time consumption, it's best to leave that to the second talk. But what I wish to state is that the nonlinear extensions of this theory have been worked out. There's still major mathematical challenges in this area, but what are called the mean field gain equations, which were developed by Minyi, Roland, and myself in Canada, and Lazare-Lyon in France, independently, that these will be presented in the second talk, and the extension of these with the major-minor players theory will also be indicated. So, and also we've indicated that the applications of this work are really very extensive, and I'd be happy to discuss all those possibilities with people here later. Okay, so thank you very much for, I'm going to say, sustaining your hunger. I realize I'm the only hungry person here because you've had lunch. So the smart thing to do is to wind up the talk and for me to get a sandwich. Okay, thank you for your patience and your attention.